Hello, hello, hello. This is Nicholas doing first and second order linear homogeneous differential equations with constant coefficients. So for first order, that would be differential equations in the form, that's an ay prime plus by is equal to 0. And looking at this equation, you would guess educatedly that the solution has to be a function so that when you differentiate it, it's just some constant times the original function. So that when we multiply the derivative by a and the function by b, that's the only way that they could cancel out and give us 0. If the derivative of the function is not a scalar multiple of the original function, then that's not possible to do. For example, y equals the fourth root of x would be a very bad guess because its derivative is 1/4 x to the negative 3/4, and the original function is x to the 1/4. So this x to the negative 3/4 and this x to the 1/4 are not going to cancel out in any way to give us 0. So we need some function that take its derivative, it's just some number times the original function. And that is equations of the form y equals e to the rt, because then y prime is r times the original function itself, e to the rt. So if we plug that in as a guess, we get ar e to the rt plus b e to the rt is equal to 0, or e to the rt times ar plus b equals 0. And since e to the rt is strictly greater than 0, we can divide by it. And so we get that ar plus b is equal to 0. And this equation has a name. It's called the characteristic equation. And what it tells you is, if you couldn't guess, it tells you what the value for r is in front of the t here for our solution. So as an example, if we have 5y prime plus 2y equals 0, the characteristic equation would be 5r plus 2 equals 0, or r is equal to negative 2/5. That's a 5, not a Raman thing. So the general solution to that equation is y is equal to e to the negative 2/5 t. The more general solution would be e to the negative 2t plus, say, c over 5. I'll call it c sub 1 over 5 because then what you could do is divide each thing by 5 and you'd get e to the negative 2/5 t plus, call the c1 divided by 5, let's just call that c. And that's the general solution to that equation. And we could make it look a little nicer too, right? Because when we in other words, when we have, say, a to the b times a to the c, that's a to the b plus c. So we could go backwards here. This is e to the negative 2/5 t times e to the c. And e to the c is, again, just a constant. So that's c e to the negative 2/5 t. And that's how you will see it written in most textbooks, c e to the negative 2/5 t. And if you do plug that into the original differential equation, you will get 0. So now let's consider second order. It works very much the same way. Let's do that's equations of the form ay double prime plus by prime plus cy is equal to 0. And so if we take the same guess, because the same guess, it should make sense that it still holds in this case. And the only way for us to cancel out the functional part here, the e to the negative 2/5 t, is if its derivative is just a scalar multiple of the original function. So I'm going to guess y equals e to the negative rt. So we get a r squared e to the rt. I took the derivative twice in my head, plus b r e to the rt plus c e to the rt equals 0. We can pull out a e to the rt. and we can divide by it since it's not equal to 0, and we get AR squared plus BR plus C equals 0. And this is the characteristic equation for the second order. And you could probably guess that for third order, it's AR cubed plus BR squared plus CR plus D. So really, finding solutions to these linear first order, second order, third order, n order differential equations with constant coefficients comes down to finding solutions to the characteristic equation is really all it is. So it really just comes down to algebra. So let's do an example here. Let's do y double prime minus 3y prime plus 2y equals 0. Its characteristic equation is r squared minus 3r plus 2 equals 0. And I just pulled this equation out of thin air, but literally all I said to myself is, what's a polynomial that factors nicely? And that's what most textbooks do, and that's how they get these differential equations. So this factors into r minus 2 times r minus 1 equals 0, so r is equal to 1 or 2. So this means that y equals e to the t is a solution, and we could have c e to the t, right? Same logic as up here, where I put the c there. C e to the t, and it's the 1t because of this one here. We could also have y equals, we'll call these y sub 1, y sub 2. Call it c sub 1, c sub 2. E to the 2t from this 2. So this isn't the most general solution. In fact, the most general solution is any linear combination of those two particular solutions. And this is true because of it's called the principle of, it's a real fancy name for something really simple, but principle of, whoa, the O just went away, superposition. And so the idea is the general solution is y equals c sub 1 e to the t plus c sub 2 e to the 2t. And you can, I probably should show plugging this in. Let's plug it in just so I can show to you that and you can prove this in general for yourself, that any linear combination, which is of this form, some constant times e to the t plus another constant times e to the 2t, that's a linear combination of e to the t and e to the 2t. We can say that the derivative is just c sub 1 e to the t plus 2 c sub 2 e to the 2t, and y double prime is still c sub 1 e to the t plus 4 c sub 2 e to the 2t. And so if we plug this into our equation, we get c sub 1 e to the t plus 4 c sub 2 e to the 2t. Now we do minus 3 times the first derivative. So that's minus 3 c sub 1 e to the t minus 6 c sub 2 e to the 2t. And then we take 2 times the original function itself, which is plus 2 c sub 1 e to the t plus 2 c sub 2 e to the 2t. And this should be equal to 0 unless I messed up on my arithmetic somewhere. So we have c sub 1 e to the t, c sub 1 e to the t, c sub 1 e to the t, and then we have c sub 2, c sub 2, and c sub 2. So we have one of these, minus 3, that's a minus 2, but then we add 2 more, so all of these go away. And then we have 4 minus 6, that's minus 2, but then we add 2 more, so those go away. So this is the most general solution to the differential equation, and it checks out. 0 is equal to 0. So that's how you can actually check that this equation does work here. And that's the general procedure. Just plug into the differential equation and find the auxiliary equation and find the roots, and